Hello student, welcome to our fourth lesson. Under this lesson, we are going to discuss latent heat of vaporization. We start with the definition of latent heat of vaporization, and this one refers to the heat energy required to change the state of a substance from liquid to gas without change in temperature. Then we come to specific latent heat of vaporization. Now, this is the energy required to change a unit mass of a substance from liquid to vapor without change in temperature. Note the difference. In here, we are just referring to amount of substance. We are not specific. But now when we come to specific heat, latent heat of vaporization, we are specific and we want a unit, 1 kg of mass. So it implies that mathematically our specific latent heat of vaporization will be given by Q over M, which implies that Q is equals to mass times specific latent heat of vaporization. From here, we can be able to get the SI unit, because now the SI unit will be given by the SI unit of heat divided by the SI unit of mass, which is joules per kilogram. We can be able to look at this graph to see how or what is happening when an object that is heated or is cooling. We have during boiling, that is when we have latent heat of vaporization, and during melting, that is when we have latent heat of fusion. And as you can see, at this particular point, boiling and melting, there is no change in temperature because the energy that is being absorbed here is used to change the state. And the energy that is being absorbed here is again used to change the state. So during these two processes, there is no change in temperature. So in here we have latent heat of vaporization. In here we have latent heat of fusion. From there, we move to latent heat of vaporization. We want to see what will happen when you have an ice or steam that is being passed in water. If you look at this diagram, we have a safety tube. We have a rubber band here that is fitted here. Then we have round-bottomed flask. We have water that is boiling. And then this water is boiling. It is giving us steam. Then the steam is delivered using the delivery tube to where we have the calorimeter. The calorimeter has a stirrer. This one is just starting to ensure that we have uniform temperature here. And again, we have the thermometer that is giving us the temperature change or the change in temperature. Now, when the steam is passed into water, the steam is passed into water, it first changes to water at 100 degrees Celsius. Remember, the steam is coming from here and it's passed here. So as it comes here, it first changes into water at 100 degrees Celsius. And then it cools from 100 degrees Celsius to the final temperature of the mixture. And the mixture will be now the water that was already in the calorimeter and the calorimeter itself. We shall get the final temperature, and that will be given by our thermometer. Then the specific latent heat of vaporization can be calculated as follows. We have that the heat lost by condensing steam, that is mass times specific latent heat of vaporization, plus heat lost by the cooling water, that is that steam that has condensed will have to lose some heat. That will be equal to heat gained by calorimeter and the stirrer plus heat gained by the water. So using this formula, we can be able to get the specific latent heat of vaporization. Now, when using electrical method, our LV is calculated as follows. Remember, all what we have now changed is the source of energy. In here, when we are using the electrical energy, we are using the heater that is applying heat. So we shall say that heat supplied by the heater coil should be equal to heat used to vaporize the water, which implies that VIT, this is the heat supplied by the heater coil, must be equal to the mass multiplied by specific latent heat of vaporization, our MLV. So that way you can either use this formula to get LV, or when you're using the method of mixtures, you can use this method. From there, we can go look at several examples. Number one, calculate the amount of heat energy required to convert 4 kilograms of ice at negative 10 degrees to liquid at 5 degrees Celsius. Here we are given the specific heat capacity of water as this one. specific heat capacity of ice and specific latent heat of fusion of that one. We proceed as follows. We know that to get the amount of heat that is required, we need the amount of heat for the ice that is changing, the amount of heat that is being required to melt the ice, and the amount of heat that is absorbed by the water. So we proceed as follows. We have the mass of the ice, then multiplied by the specific heat capacity of ice, and then we have the change in temperature. Because the ice was at -10 and it is coming to 0, then that will be 10 minus 0 to get 10. Then we come to the amount of heat that is required during the process of melting. That will give us the mass of ice that is given there, 4 kg, then multiplied by specific latent heat of fusion that is given as 340,000. Then after that, after the ice has melted, that water has to rise, and it is rising up to 5 degrees Celsius. So that is where now we are saying there is heat gained by the water. So the mass will be the same, 4 kg, multiplied by the specific heat capacity of water, then the change in temperature, that will be 5 minus 0 degrees, because that water is coming from 0 degrees to 5 degrees. When you multiply all these values, this part will give you 84,000, then this will give you 136, or if you look at what we have here, it is 1.36 million, or 1,360,000. Then from there, this part will give you 84,000. When you add, you get that it will be 1,528,000 joules, or what we call 1.52 m, or 1.528 megajoules. That is the amount of heat energy required. We look at example 2. A kettle rated 4 kilowatt containing 2.0 kilogram of water is left switched on. How long will it take the water to boil dry in the kettle if the initial temperature of water was 20 degrees Celsius? And then you are given the specific heat capacity of water as 4200, specific latent heat of vaporization as 2.26 times 10 to the power 6 joules per kilogram. We proceed as follows. The quantity of heat that is required or that is supplied is given by power times time, and that heat must be equal to the heat gained by the water and the heat amount, or the amount of heat energy required during process of melting. So we proceed as follows. You have praised the power 4,000 times time, that is kilowatt. It is 4 times 10 to the power 3, so it is 4,000 times time. And the time here, we are told that it is how many minutes? If you look at what we are saying, it is just left switched on. How long will it take? So we are looking for this time. So we come here and we insert the other values. Mass of water, again, is 2 kg multiplied by 4200, that is specific heat capacity of water. Then the change in temperature. It is coming from, it is boiling, so at 100 degrees, and then it is, the initial was at 20, so the change will be 100 minus 20. Then after that, you have the amount of energy required during melting. You have 2 kg multiplied by specific latent heat of vaporization, that is during the evaporation. Then from there, this part, when you multiply 2 times 4200 times 80, you get 60 or 672,000. And when you multiply this, it will be, if you look at this value, it will be 4,520,000. And then this other part, it will be 4,000 multiplied by T. So to get the T, you divide through by 4,000. When you divide, when you add and divide, you'll get that it will be 1,298 seconds. That is 1,298 seconds. That will be the time taken. Then from there, we move to another example. Given that the specific heat capacity of steam is that one, specific heat capacity of water is this one, and the specific latent heat of vaporization of water is this one, specific heat capacity of glass is given as that one. What mass of steam initially at 130 degrees Celsius is needed to warm 200 grams of water in a glass container of mass 100 grams from 20 to 50 degrees Celsius. We proceed as follows. This is the method of mixtures. So we are saying heat lost by the condensing steam plus heat lost by cooling water should be equal to heat gained by the glass plus heat gained by the water. So we proceed and put the values. You have the mass, this one is during the condensing, the mass multiplied by the specific latent heat of vaporization, then the mass, that is what we are looking for, multiplied by specific heat capacity of water, change in temperature. Remember, the temperature is coming from 130 degrees to 50 degrees. The steam was coming from 130 to 50 degrees. So when you subtract there, you get that it is 80. Then there was glass. The glass initially was at 20 degrees. So, and the final is at 50. So the mass of the glass is given as 100 grams. So that is 0.1 times the specific heat capacity of glass is given as 840. Then multiplied by the change in temperature. Then the heat gained by the water, you have 0.2. Then multiplied by 4200. Then multiplied by 13. From there, we multiply this and then we add, you get this value. And when you multiply and add, you get that it is 27,720. To get M, you get now, you divide through by this. This is 2,596,000. You are taking 27,720 divided by 2,596,000. And when you divide, you get 0.01068 kg. That is what we are getting as the mass. Then from there we proceed to another example. Water at 24 degrees falls through a height of 72 meters to the bottom of the dam. Calculate the temperature of the water at the bottom of the dam. What you're supposed to note here is that the energy possessed by the water will be the energy gained by the water, because we say that energy can never be created, neither can it never be lost, but it is being converted from one form to the other. So the energy that is possessed by the water at this height is what we call the potential energy, and it is given by mgh. And then now the heat gained by the water will be given by mc, change in temperature. So the mass multiplied by the time, 10, that is g, multiplied by the height, will be equals to the mass multiplied by the specific heat capacity and then multiplied by the change in temperature. This mass and mass will cancel out because we are referring to the same amount. So we are left with the 720 here. Then we have 4,200 multiplied by the change in temperature, which implies that the change in temperature, that is theta minus 24, will be equal to, you're supposed to divide through by 4,200, you get 0.1714. When you add and you divide, you are going to get that the value of theta will be 24.17 degrees Celsius. This should be degrees Celsius, not 170. So that way, this is now the final temperature of our water that has fallen from the dam or from the fall. Then number 5, calculate the quantity of heat required to completely convert 0.5 kg of ice at negative degrees Celsius steam to steam at 100 degrees Celsius. Then take specific heat capacity of fusion of ice as that one, specific heat capacity of water as 4,200, and specific heat capacity of ice as 2,100, and then specific latent heat of vaporization is given as 22.6 times 10 to the power 5 joules per kilogram. We proceed as follows. The total heat required will be given by the heat that is required to raise the temperature of ice, the heat that is required to melt the ice, the heat that is raising the temperature of the melted ice, and the heat that is required during the process of vaporization. Now, the heat required to raise the temperature of ice from -6 to 0 degrees will be given by Mi, that is the mass of ice, specific heat capacity of ice, and change in temperature. And that one, when you multiply 0.5, that is the mass of ice, multiplied by 2,100, specific heat capacity of ice, then multiplied by the change in temperature, that is from -6 to 0, you get that it is 6,600 or 6,300 joules. 6,300 joules. Then from there, heat required to melt the ice will be MLF, where m is the mass of the ice and Lf is the specific latent heat of fusion. And when you multiply, because the values are given there, then you get that it is 168,000 joules. And heat required to raise the temperature of water, that water that is gotten from melted ice, it is at 0 degrees. It will change from 0 to 100. Therefore, it will be 0.5, that is the mass, multiplied by the specific heat capacity of water, then multiplied by the change in temperature, which is 0 to 100. When you multiply that, it becomes 210,000 joules. Then heat required to completely vaporize the water, that is our Q4, it will be mLV. And that is the mass, then multiplied by specific latent heat of vaporization, to get that it is 1,130,000 joules. Therefore, the total energy required is the sum of all these energies. You take the first one, 6,300 plus 168,000 plus 210,000, then plus 1,130,000. When you add, you get that it will be 1,514,300 joules. That will be the energy required to convert that amount of ice to vapor at 100 degrees Celsius. From there, we have the assignment. Again, this one is testing what you have just learned. So make sure that you revisit and you discuss with your peers, because when you discuss, when you share the knowledge, that knowledge will be multiplied. So thank you, and let us meet in our next lesson.